Every person has taken math in school sometime in their life, but why don't we have a clear definition of mathematics? What on earth are we studying? What kind of education puts you through 12 years of math and doesn't even explain to you what it is? Galileo said, "If I were again beginning my studies, I would follow the advice of Plato and start with mathematics." Einstein said, "Pure mathematics is, in its way, the poetry of logical ideas." You don't need to know anything to understand this lesson. You only need a rational mind. You might be asking yourself, why should I bother know what math is? Well, because it's the most precise and accurate language ever, because it's the most systematic and logical branch of knowledge humans ever conceived of, because science and engineering are ridiculously vague without it, and finally because you have a course on it and you want to actually understand it. Before you learn any branch of knowledge, you have to understand that every knowledge is knowledge of something, not just knowledge, period. This something is a form of being, which has different forms of becoming. Beings are unique sets of states. Becomings are changes of states. The branch of knowledge that deals with understanding being and becoming is called ontology. So what we ought to understand is what are the objects of mathematical knowledge, and what is mathematical knowledge the knowledge of. Then we ought to know what method do we use to know these different beings and becomings. How do we acquire knowledge about these entities? What fields and topics does this method cover, and what are the limits of this unique method of knowing? So we ought to know what are the methods of mathematical reasoning and knowledge, and what is the form of knowledge we use when we do mathematics. We will approach this by discussing 5 distinctions in ontology and epistemology. The first one is abstract versus concrete entities. The second one is idealism versus realism. The third one is rational versus empirical evidence. The fourth one is deductive versus inductive reasoning. And the fifth one is synthetic versus analytic statements. Let's get started. The first thing we have to understand is what is the difference between an abstract entity versus a concrete entity. Plato says, geometry existed before creation. What does he mean by that? Let's start with some definitions. A concrete entity refers to a thing that exists physically. An abstract entity refers to a thing that is not necessarily physical. It is a type of thing or just an idea. Physical means within space and time. So, abstract entities don't necessarily have an existence in space and time. Note that abstract ideas may or may not have their concrete particular counterparts. For example, the idea of a snake is an abstract idea, but that doesn't mean that there are no snakes concretely. The idea of a unicorn is an abstract idea, but that doesn't mean there must be some unicorn existing concretely somewhere. Zeus doesn't exist, but is he still all-powerful? Well, the abstract idea of Zeus entails by definition an all-powerful being. There is no concrete Zeus who actually exists. So when we're talking about Zeus concretely, he is non-existing. And if something is non-existing, you can't say it's all-powerful or weak. So concretely, Zeus is not powerful or weak, but abstractly, he is all-powerful. Mathematical entities are abstract entities that may or may not have concrete counterparts. On the other hand, scientific entities are concrete entities that we study abstractly. So in mathematics, we start with abstract ideas, like real and complex numbers. Then we can, if we want, look into the real world and look where we can apply them concretely. On the other hand, in science, we start with concrete entities like solids and fluids. Then we can abstract away from them and go into the realm of mathematics. The second distinction we have to understand is idealism versus realism. Einstein said, "How could it be that mathematics, product of human thought independent of experience, is so admirably adapted to the objects of reality?" Let's start with some definitions. Idealism in metaphysics is the position that what you know about an entity is dependent on the mind. Thus, what you know about an entity does not necessarily exist independent of the mind. Realism, on the other hand, is the position that what you know about an entity is dependent on the entity. Thus, what you know about the entity is independent of your mind. It seems that our knowledge of mathematical entities and their properties is dependent on our minds rather than these entities by themselves. For abstract ideas are entirely dependent on the mind conceiving them, not their actual existence in the real world. So we can go back to Euclid's definitions and axioms and alter them, and our new systems of geometry won't be more true or false than the old systems. Both systems are correct as abstract systems. Some of them may be more or less applicable to the concrete world, but that doesn't mean they're more right or wrong. On the other hand, scientific entities and their properties seem to have an existence independent of our minds, for they are initially concrete entities in the physical world, which seems to follow its own rules rather than our own rules. So, in scientific knowledge, if we alter Newton's theories of gravity due to a new observation or experiment, our new understanding of gravity is indeed more true and correct than the old understanding. The third distinction we have to understand is the rational versus empirical evidence distinction. Rational knowledge is knowledge independent of our senses. Claim that is a priori is independent of experience. On the other hand, empirical knowledge is knowledge dependent on our senses. Claim that is a posteriori is dependent on experience. Mathematical knowledge seems to be entirely independent from our senses. We might get inspired through observing things in nature to study geometry, for example, but all geometric claims and propositions and theorems are entirely independent from sense data. Thus, mathematical propositions are all a priori. On the other hand, scientific knowledge seems to be entirely dependent on our senses, for without observation in nature or through experiments, no scientific theory would be. Observation means that we are collecting sense data. Of course, the analysis of this data is entirely rational, but the point is you cannot have a scientific claim or proposition or theorem that is entirely independent of sense data. Thus, scientific propositions are all a posteriori. The fourth distinction we have to understand is the deductive versus inductive reasoning one. Bertrand Russell says, mathematics takes us still further from what is human into the region of absolute necessity, to which not only the actual world, but every possible world must conform. Then Whitehead says, mathematics in its widest significance is the development of all types of formal, necessary, deductive reasoning. To get started, we have to understand what logic is. Logic is the method of connecting premises to conclusions using a set of laws. It is a method of using some knowns to know some unknowns. The knowns are called premises, the unknowns conclusion, and what is in between is called logic. In order for a statement to be true, its premises must be true and its logic must be true. If a statement's premises are false, then we say the statement is incoherent. It's like having the wrong data and analyzing it perfectly. Even though the analysis was perfect, the conclusion is still false. If a statement's logic is false, then we say the statement is inconsistent. It's as if you had perfect data and you analyzed it in the wrong way. Even though the data was perfect, the conclusion is still false. And deductive reasoning is a specific type of logic where the conclusions necessarily follow from the premises. Necessary truths mean that there is no uncertainty or probability involved. If all the premises are true, the conclusions must be true. For example, all men are mortal, Socrates is a man, is true. Then it necessarily follows that Socrates is mortal. On the other hand, inductive reasoning is a specific type of logic where the conclusions contingently follow from the premises. Contingent truths mean that there is some uncertainty or probability involved. So, in order for the conclusions to be true, you need some conditions to occur. For example, given the premises we heated 1,000 metals, they all expanded. It doesn't necessarily mean that all metals expand when heated. It is indeed probable that all metals expand when heated, but it's not necessary. Why? Well, because we only tested 1,000 metals from all the infinite metals in the universe. Mathematical reasoning is deductive reasoning with necessary conclusions. On the other hand, scientific reasoning is inductive reasoning with contingent conclusions. The fifth and final distinction we have to understand is the synthetic versus analytic distinction. Analytic propositions get their meaning from themselves. For example, all bachelors are single is an analytic statement. By the definition of the word bachelor, we understand that these people are also single. On the other hand, synthetic propositions get their meaning from the world. For example, all bachelors are unhappy. Within the concept of bachelor, you don't necessarily have unhappy. In mathematics, propositions are sometimes analytic but mostly synthetic. So when you analyze a proposition like 12 equals 3 plus 9, no matter how long you analyze the concept 3 or the concept 9, you won't find the concept 12 within them. But if you rely on your intuition or start representing 3 and 9 using your fingers, you see that they become 12. Another proposition is the shortest path between 2 points in space is a straight line. No matter how long you analyze the concept 2 points in space, you won't necessarily find the concept the shortest path is a straight line in between them contained in it. You have to actually rely on your intuition or start representing points in space and measure distances and draw lines, and then you realize that the statement is actually true. In science, propositions are also sometimes analytic but mostly synthetic. Typically, the synthetic ones are the actually useful ones. For example, F equals ma. No matter how much you analyze the concept of force, you won't necessarily find mass and acceleration inside of it. But if you go out in the real world and you observe things, you would realize that indeed force equals ma. Okay, after understanding the 5 distinctions we talked about, we can now give a more accurate and precise definition of what math and science are. So, mathematics is the study of necessary synthetic truths through rational, deductive reasoning on abstract ideal entities. On the other hand, science is the study of contingent synthetic truths through empirical inductive reasoning on concrete real entities. Every single thing I said, from the definitions to the claims about math and science, is controversial. So there is some thinker out there, dead or alive, that would actually disagree on every statement I had in this video. But this is the best explanation I could provide on what is math in 15 minutes. Every branch of knowledge could be divided into more specific studies. For example, we can divide math into pure versus applied math. Then we can divide pure math into the study of quantity, structure, space, and change, and applied math into computational methods and statistics. The reason I didn't bother explain this is because everything is interconnected. For example, calculus is the study of change, but it requires understanding functions in algebra, and also numbers, and some geometry. So therefore I decided to ignore explaining the subdivisions of mathematics. Finally, I would like to conclude this video by explaining again why one ought to know this. See, when you study physics and you go through all the course materials on Earth and you ace every exam, but you don't understand the observations and experiments and the concrete entities you're studying, you're not a physicist, nor do you have a physicist's understanding. In other words, you missed the whole point of studying physics. And if you're studying math and you go through all the course materials on Earth and you ace every exam, but you don't understand the rational deductive reasoning that causes each theorem to be true, then you're not a mathematician, nor do you have a mathematician's understanding. In other words, you missed the whole point of studying math. The same thing can be said about every branch of knowledge, physics, biology, engineering, etc. If you don't know what you're studying, then what the hell are you doing? Now you may ask yourself, why don't they teach you in school what math is or what physics is? The answer is pretty simple. Schools don't try to produce Leibniz or Newton or Leonardo da Vinci. Their goal is to produce tame, domesticated animals to feed the production forces at the given time and place. So the most important benefit from knowing what science is or math is now we know exactly how we should approach it, how should we study it, how should we teach it, which is the topic of my next video. Finally, if you had any problems understanding some of the concepts, then I advise you to go online and look up philosophy encyclopedias like the Stanford one and search the concepts you didn't understand. If you're feeling lazy, you can ask questions in the comments section. Please like, share, and subscribe. Thank you for watching.